That's
Right, you want to start with something?
You want to start with just any of them?
We can start with 3 then.
Yeah.
So what's exactly? So it's an infinite line of charge with linear phase, between long axis, I think insulating. Oh, and a radius. Linear dot times what is the value of the x component of the electric field? Okay. Well, this is 2 cylinders, right? That's a line of charge. This line has lambda 1. This line has lambda 2. And they want the electric field somewhere here.
They want that electric field like 5.
At point x.
5 and 0.
Point P.
Yeah.
Okay. 5 and 0 or 0, 5?
0, 5. Yeah. So where is it?
This is point P and this is D. Oh wait. All of these problems, when you have a distribution of charges, you always begin with Gauss's law. Now, you can easily do them because he always tells you in class to imagine that it's a line and use the line formula. You'll end up with the same result. Line formula. You know the line formula? It's on the working sheet. Also.
It's like 2K or whatever.
Exactly, 2k lambda over r, r being the distance from the point. But sometimes they're not going to give you lambda for a line, they might give you q for a line. So you have to convert that into lambda. The easiest way to do that is using Gauss's law. So I'm just going to do it with Gauss's law because it's a more general case than having that line formula. So with Gauss's law, what Gauss's law tells you is electric flux for epsilon naught, right? This tells you that the flux, this entire quantity is the flux. It's proportional to the charge enclosed, right? But the flux has an E in it. So the entire idea of using Gauss's law on a question like this is to try to solve for E, right? So what does this symbol says? This means around a closed surface. So that's why we need a Gaussian surface for this. This is your Gaussian surface. It's also going to be a cylinder with length L. Doesn't matter the length. The length is going to end up canceling out. So just assume an imaginary surface engulfing that line that you have, an infinite line, and you apply Gauss's law to it. Now, there are 2 important things. There are 2 requirements to applying Gauss's law. This is a hard integral. You can't integrate this. Sometimes you can't integrate this. For example, if you have a charge here, Q1, and you have a charge here, Q2, and you use your Gaussian surface like this to determine the electric field at this point P, you can't integrate this. The reason, because this is going to have an electric field pointing this way, and this is going to have an electric field pointing this way. So the electric field is not uniform throughout the surface. It's changing from here to here to here to here. Just look how it is here. Here it's going to be pointing in that direction. Here it's going to be pointing in this direction, right? So you can't break this integral down like you do it if you don't have a symmetrical charge distribution. In this case, we do. In this case, all the field lines are pointing outward. All the field lines are pointing outward and are making right angles with the Gaussian surface that we have. That means we can get rid of the dot product here. So that integral becomes E times dA equals Q enclosed over epsilon naught. Now, since this radius is the same as this radius, that means the electric field is uniform throughout the entire Gaussian surface, which means we can get rid of the integral because you're basically integrating constant. You're integrating constant, so the result is going to be dA equal to Q equals over epsilon naught. That's the first step. Get rid of that if it's a symmetrical charge distribution. Then you solve for E, because that's what the question's asking for. They want E. Q equals over epsilon naught. Now just remember what each variable is. A is the area of your Gaussian surface, the surface area of the Gaussian surface. That's your A. Q enclosed is the charge enclosed in the Gaussian surface, and epsilon naught is constant. We're going to change. So these are the 2 things you always want to find. What's Q enclosed inside the Gaussian surface? We said it's a cylinder with length L. Oh, it doesn't look like a cylinder here. That's your Gaussian cylinder. So we want the charge enclosed in this. That's the first thing you want. The second thing you want is the surface area of this. Now to find the charge enclosed, they're giving you the charge only as a function of lambda and lambda 2. Right? You want to turn that into a Q. What is lambda?
Linear charge.
Linear charge density, which means Q over A. Right? Now, like in chemistry, when they give you density of something, like the density of metal is this much. If you take a small quantity of metal or a big quantity of metal, density is going to be the same. Mm-hmm. Here's the same thing when they tell you a constant linear charge density. So it's going to be the same. So if you take a big area, it's going to have a big Q. If you take a smaller area, it's going to have a smaller Q. That's the Q enclosed. If this is the area enclosed, this is the Q enclosed. Oh, sorry. L. Lambda is the length. Lambda is the length. Sigma is Q over A, which is the surface charge density, and rho is Q over V, which is the volume charge density. This is the charge distributed over the length. This is the charge distributed over the area. This is the charge distributed over the volume. I'm not sure if those are in the equation sheets or not.
Yes.
Is it?
Yes.
Lambda, yeah. Okay. So back to what we were doing. We were trying to get Q enclosed from this equation. We have lambda. Lambda is given, right? Mm-hmm. We want this. So if we solve for Q enclosed, that gives you lambda L. What's L in our picture here?
Isn't the length to the Gaussian surface?
Length of the Gaussian surface, because that length determines how much length of the inner body is enclosed. So we can rewrite this as E equals lambda L over A epsilon naught. Now all we have to do is find A. That's the last thing. What is A?
It's the surface area of the Gaussian.
Surface area of the Gaussian surface. Do we take these surfaces?
No, they're
just the sides.
Just the sides.
Why?
Because since it's a line, like the field radiates outward.
We
So
don't take the surfaces that have no electric field going through them. Only the surfaces that do have electric field. Those are the surfaces we take.
And that's flux, right? Or like when it passes through the surface? Or am I completely off?
Kinda, yeah. Flux is basically, they define flux as the number of lines.
Oh, okay.
I mean, it's not exactly a very good definition because you can assume the number of lines whatever to be, but okay. So yeah. So flux relates to an entire surface. So if you have, so you can say that the flux through this entire cylinder is this much. You can also say the flux through this surface is this much, but the flux through this surface is always zero because there's no electric field conflict. So yeah, basically it's. So A is equal to the surface area of the sides of the cylinder. The surface area here on the sides. We chose our Gaussian surface to have a radius of d, which is the same distance of the point from the center. So that's a radius. So area is 2 pi d times L, length of the cylinder, right?
Why is it 2 pi d?
Because
Because you got the inner surface and outer surface.
No, the radius, the area.
The area is pi d. Oh, okay.
The circle.
You're saying the circumference?
Circumference. I mean,
Oh,
circumference of the circle is 2 pi.
it's 2 pi r or
2 pi
pi
r.
d. It's either pi d
2
or
pi r.
2 pi r.
2 pi r.
2 pi d.
2 pi r.
But they're saying D is R.
D is r.
In this
D is R.
In this case, D is r.
Okay, I'm clear now.
Okay. So we just substitute the area that we have here. E is equal to lambda L over 2 pi d L epsilon naught. These are always going to cancel out because it's not exactly a quantity you specified. You're just picking an imaginary surface that has an imaginary length. And you're always going to end up with vowels here and here. So that gives us the same equation in this case of the line, because we said it's 2k lambda over r. I don't know where it went. So since 1 over, we can multiply this by 2 over 2. 1 over 4 pi epsilon naught is equal to k, right? So that's lambda times 2. This is 4 pi epsilon naught. Well, there should be a d also here. 2 pi, so k over d is equal to e. That's the same equation you end up with the line. That's how they derive it, basically. And the question gives you 2 lambdas. So you really don't have to go through this entire process if they give you lambdas. If they give you something like rho, then your charge, either volume charge,
Volume density.
is it volume density? Volume density or surface charge density, it's going to be easier for you to convert onto compose through that.
If they gave us like rho or whatever, couldn't we just convert it into?
You can't convert it into lambda. You can directly also convert it into lambda.
And then just plug into.
Plug it in instead of lambda.
Okay.
And it works the same way for the other two, for the sigma
For sigma.
and the P.
The rho, yeah. Sigma you can also convert it through dividing over length. Don't quote me. But yeah, I mean, you can figure it out by converting first to Q, then to L. That's easier. But yeah. So we have lambda and lambda 2. This is the arithmetic sum of them. So if it's positive, negative, you just add the positive 1 plus the negative 1. So positive 1 minus the magnitude of the negative 1. You end up with the lambda that you're using in your calculations. And that'll give you the electric field at distance d. So what do you have for lambdas here, for example?
The first one's 3.2 and the second one's negative 7.6.
Okay. So what we do is, this is the practice test for by the way.
Yeah.
If you don't have, I can pull it off, pull it on the screen if someone doesn't have it.
You can put it on the screen.
All right, I'll put it on the screen after this question. This question just gives you 2 little lambdas. Like, you have an insulating cylindrical shell and a line, and they ask you for the electric field at a point P. That's what the question is. I'll pull it off on the screen. All right, so if you have the first lambda is 3.2 positive microcoulombs minus 7.6. That's times k times 2 over the distance that you have, which is 5 centimeters. So 5 times 10 to the negative 2, that's what's in centimeters. And this is times 10 to the negative 6 instead of micros.
And that's the value for
The electric field. And it's pointing in the y direction.
So that would be the answer for if they ask for the y component.
Basically, yeah, because there's only a y component in that direction.
And
If the point was here, and they asked for the y component, let's assume the distance is the same. If the point was here, and the point was here, P, and they asked for the y component, this answer would not give you the y component. This answer would give you the electric field in that direction. It would have a y component like this, an x component in that. They would most likely give you a theta here. And you do sine the answer to get the y, cosine the answer to get
But like for the original one that is vertically up, if they ask for the x component, it'd be 0.
0.
Yeah, because that's what it asked for.
If it's on here, so if it's like 5, 0, it's only going to happen x component. It's not going to happen 0. And y component is 0. You done with this, or is there something else on this question?
Yeah, that's what it's asking for.
So,
So I'm just switching classes. This is the one in class. Right here.
lambda 2. That's the same thing, yeah.
Right, so I can just use this right here.
You can use it exactly the
Cosine
same thing.
30
Cosine
degrees.
30, that'll give you the y component,
But
right?
not the x component.
It depends on where your theta is. So if theta is here, if they're saying this is,
Okay.
I assume that they're saying cosine always gives you.
60.
So when you have a vector, let's forget about the x and y axes for a second. If you have more questions, tell me. If I don't explain exactly what you want. So let's assume you have two vectors. It doesn't matter if they're x or y. You have vector v1, and you have a vector v2, right? And you have a theta in between them. And you want, now, v1 here, since theta is not 90 degrees, this is not equal to 90 degrees, v1 is going to have a component that's parallel to v2. Because if you draw it this way, this is v1 that's parallel to v2. And this is v1 that's perpendicular to v2. When you say the cosine of the angle between two vectors, that's going to give you the component of that vector that's parallel to the other. That's the same thing. That's basically what we're doing when we say we have an x, y, and we have a vector here, v, and we want the x component of that vector. Cosine this angle gives you the x component, and sine of this angle also gives you the x component. Also, we can take cosine of this angle to go here, and sine of this angle to go here. Right? Cosine of the one in between. I'll give you the. Is there something else about the question?
So the question is, what's not 60 instead?
Cosine of 60 again is to go to x, right? Oh, the one. You want the electric field at point P? Px is going to be the result that you get. You don't have to get cosine, right? It's going to be pointing in the x direction. If it's at point R, depending on the magnitude, negative one, not negative one is greater, so negative and positive.
You gotta, that's like,
Distance is equal to magnitude of that, so yeah, 10.6. That's the distance. The electric field is going to be pointing, since the entire body is charged negatively, right?
Yeah.
Negative is greater, right? So it's going to be pointing towards this one, towards the center.
So,
It even changes it, but it can't insulator.
For this, no, because there is no y component for this. There's only an x component, right? For the other one, if they want the y component, it's cosine 30. The x component is sine 30. Or, as you said, cosine 60 and sine 60. Can I? Is there no internet again?
Do you ever see to that one, by any chance? See?
yeah, that one says draw the electric field both outside of and inside of the insulating shell.
Okay. Alright, I'll just draw it again. This is our insulating shell. So they want the electric field inside and outside the insulating shell. Do they mean inside here?
No, there's nothing inside the, well, that's the insulating shell.
That's inside the. I don't think he means that because that's going to complicate us. We'll do it both ways though. This is not going to be easy if he does so, especially if he wants it to be precise. Look why. What's lambda 1?
3.2.
positive, right?
Yep.
Lambda 2 is
Negative 7.6.
negative 7.6. He wants you to draw the electric field. Now let's forget about, we'll just draw it here and here at first. Now inside,
3.2.
you're right, there's no electric field. The only electric field comes from this charge. The only electric field inside here comes from this charge. Because if you want to take a Gaussian surface anywhere inside here, the only charging pulse is going to be here. So that's a positive electric field. That is pointing outward from the point. So that's the direction of the electric field inside. Outside, the total charge is 3.2 minus 7.6. That's negative, right? So the entire body is negative, so all the electric field outside is inward, right?
So that's all we had to do, just draw the lines?
Basically, yeah.
Okay.
Isn't that what the question is?
Yeah, it just says draw the electric field outside and inside.
Now, if the question wants to be silly, he'll ask you to draw it inside the insulating shell as in here. Because what happens inside the insulating shell? Here it's positive, right? It's an insulating, not a conductor, so it has an electric field. So if you take it, if you want to find the electric field at this point, you're going to take a Gaussian surface here. If you want it at a further point, you're going to take a bigger Gaussian surface. Now, as you're increasing the size of the Gaussian surface, more negative charge is enclosed. So at first, the electric field is going to be pointing in that direction. The further you go, the more negative charge you have enclosed. Eventually, the negative charge enclosed is going to be equal to the positive charge enclosed. The electric field is going to be zero. And then, when you increase more negative charge is going to be enclosed. And then, it's going to be pointing inward. So some of that electric field is going to be zero, some of it's going to be pointing outward, some of it's going to be pointing inward. He's probably not going to answer about that.
Okay.
Because you're going to have to find the exact place where it's actually pointing at zero and draw an electric field. It's not it's not a straightforward one. Can I just pull it up on the screen? Do you mind if I send it to my drive?
We need some capacitors.
Sure.
Or the homework.
Sure. Oh, thanks. I'm dry right now. It's not working right now.
Not the precious paper.
All right. I'm just going to get on the capacitors questions until that internet comes back on.
We should put it really hard one. Complex one.
Want to do this one?
Arc.
Yeah?
I think number 4.
What did they ask for? What is Q2, the charge on C2? Okay.
To do that, you have to find the capacitance everywhere and then the total charge and...
It's an annoying process. There are shortcuts. I don't think he'd like I don't think he'd like it if you use it. Because he always says...
Is there a ratio?
There's a ratio. There are a lot of circuit shortcuts that you can use here. But I'm going to go the same way that he uses.
Sorry.
No, it's fine.
Classes.
It is, but...
If you want the total charge, I have it, but I just want to know how you find it.
Yeah, that's fine. Let me just do split screen for now. So you have... just gonna Actually, I don't want to redraw it since we already have this here. So we'll just go straight ahead and do it. Let's do this. So, he's only going to give you combinations of capacitors in series and parallel. There are also other combinations that you don't need to know for this course. So, series, parallel, series, right?
It's series and then series again.
Yeah, but I mean, 3 in series is okay. So if you're having trouble with that, I don't assume you are. If you are having trouble with that, after every simplification, redraw the entire circuit. It makes stuff easier. So first we want to do C2 and C3 in parallel. That's C2 times C3 over C2 plus C3. That's how you do it, right?
No,
That you're doing the ratio method.
1 over C2 plus 1 over C3.
1 over C equivalent is equal to
Yeah.
1 over C2 plus 1 over C3. Common denominator. C.
I've dealt with him before, and he don't mind if you do the ratio. I mean, if it makes sense, because you could say what you had at first C2.
It's the same thing as finding a common
Yeah,
denominator.
plus C4.
Multiplying this by C3, you get C3 over C2 plus C3. Multiplying this by C2, you get C2 over C3 times C2. C2 over C3 times C2. 1 over C equivalent. If I put 1 over the entire thing, that's C equivalent is equal to C3 times C2 over C3 plus C2. We go ahead straight forward and do that. That he doesn't mind. I know he doesn't mind.
Okay, then we just do plus C4.
Huh?
So then 2, 3, 4 plus C4.
Yeah, plus C4. So I'm just going to use it this way.
Okay.
It simplifies stuff. It makes life easier. Okay. So let's call it C equivalent 1 is equal to C2 times C3. That's 2.4 times 5.7 over 2.4 plus 5.7 equals to not much phonetic right here.
I got it.
Got it?
Yeah, I got it. I do got it.
Okay, I'm just going to leave the feature.
1.69.
Seriously?
I'm sorry.
Michael.
I need to remind us on milk. I
Okay.
actually my class.
Two capacitors in parallel, we add them, right? So this plus C4, so let's call it C equivalent 2, is equal to 1.69 plus C4, which is 4.4 is equal to
6.
6.08.
1.9, right?
Yeah.
Microfarads. Now our circuit is basically because we simplified this entire thing into one capacitor. And we have these three. This is the value. We have these 3 in series, and we just do the same thing. 1 over C, 1. You can't use this for more than 2.
What?
These. This. So yeah, just use 1 over C. Never mind. Forget that I said anything about it. 8 times over plus. So it's 1 over C1 plus 1 over C2 plus 1 over C3. C1 is
2.1.
Why is it different here? I have a different number in my
Yeah.
phone. But anyway.
It's also changed.
This is my
Yours
one.
might be the same as mine as far as
Oh, okay.
size.
1 over 6. And you get C equivalent. I'm not going to waste time finding it. So let's assume a value for it. C equivalent equals 4 microfarads somehow. That's C equivalent for the entire circuit. That's the capacitance for the entire circuit. And you want to reach somehow for the charge on this, right? We know that
Actually two.
on
Two
2.
CD.
Okay, it's the same thing. But yeah, 2. We know that for 2 capacitors in series, the charge on this is going to be the charge the same as the charge on that, right?
Yeah.
For 2 capacitors in parallel, the voltage on this is going to be the same as the voltage on that. So if you have, yeah, it's not parallel. The voltage across this capacitor here is the same as the voltage across this capacitor, right?
Yep.
Right. So we want to use that fact, those 2 facts, sorry, to find charge on this. We start out from here. This is what our circuit looks like. Looked like at the end. We know that the voltage of the battery is 12 volts. That is the voltage from here to here, which is the same as the voltage across the capacitor. That's also 12 volts, right? That's 12 volts. So look back to what we did. This was 3 capacitors. So we know that the voltage across, So this was 12 volts. We know that the capacitors in series have the same charge. So we find the charge of this capacitor. What's the charge of this capacitor? C equals Q over V, so C equals Q, right? We find Q1. Let's say Q1 equals to 1.7 microcoulombs. That's the charge here.
Wouldn't Q total, the total charge,
The total charge on everything, yeah.
wouldn't that be the same as C1, the total charge as C1? Which would be the same.
The same charge as these 3.
Okay.
So the charge on the total one is the same charge on this 2.
Yeah.
So the charge on this is equal to the charge on that, is equal to the charge on this. Right? So we don't care about these 2, we only care about this one. We found the charge of it. So the charge of this one, the voltage across this one is the same as the voltage across A and B. So when we find the voltage of this guy here, that's V equals Q over C. Let's assume we got, I'm going to call it VAB. It's VAB.
Are the voltage the same? After, like...
Voltage across here is the same as the voltage across here, which is the same as the voltage across here. When you're expanding in parallel, the voltage stays the same. When you're expanding in series, the charge stays the same. You have this capacitor to be the equivalent capacitor of these 2. And you know the charge on this is Q. The charge on each one of these is Q.
Yeah.
Right? And the same thing with the voltage across to so if you have,
What would be different then?
what will be different?
Yeah.
The
From
voltage of these is
C2
different.
C3,
The voltage from here to here is different than the voltage from here to here because the capacitance is also different.
Okay, that's okay.
If the capacitance was the same, they would have the same voltage.
No.
Because they have the same charge. C
Oh,
equals
yeah,
Q over
that's
V.
right. That's if they have the same charge.
If they have the same, no, if they're in series, they're always going to have the same charge. But if they have the same capacitance, if they have the same C. So if this is 2.1 microfarads and this is 2.1 microfarads, the voltage across here is going to be the same as the voltage across here, right? All right, where were we? Last thing we did is we found the voltage across A and B, right? So we know that the voltage across this entire thing is, we call it VAB. It's not a very anymore. We want to find we already found the equivalent capacitance of this entire thing. It was 1.69 for these 2, right? So again, C equals Q over V. We want the charge because they're in series. So Q is equal to VAB times C, which is 1.69, whatever it was when we found it.
Yeah.
Microcoulombs. That's the charge on the equivalent one, which is also the charge on the top one, which is also the charge on the bottom one. Right? And that's what they want.
To find V at C2, V23, which is VAB.
VAB, yeah. Fine.
I was really stuck here and I don't see my problem.
Right. So, last thing we did, let's go back to when we had only one capacitor. This is the equivalent capacitance of all capacitors.
And the V is 12.
V is 12. We know that the voltage across here is equal to 12 now, right?
Yeah.
Let's find the charge on here. We call it Q total. And let's put it back to 3 capacitors in series. That's a step that we did. Sorry. That's a step that we did before. There are 3 capacitors in series.
That's where the volt changes, doesn't it?
Voltage from here to here is still 12. But the voltage from here to here, here to here, here to here is different. But the charge on this is Q total. The charge on this is also Q total. This is also Q total.
Okay.
So we know the charge here is Q total, right?
Yeah. And so to find the...
This is also AB, because this capacitor came from this combination of capacitors, right?
How would you find the volt at that point?
A to B,
Yeah.
different.
Yeah. The volt there, so you could break it down to find the charge at C2 with the VAB.
Charge at C2, the VAB. You mean the voltage of AB? Voltage difference between A and B? Is that what you're asking for?
Yeah.
Yeah. So we know, we said this is Q total. This is also Q total. This is also Q total. We know the equivalent capacitance of these to be 6.09. C equals 6.09 microfarads. C equals Q over B. Solve for B. C and Q.
Would it make sense if we wrote the whole equation out? And then put
I got it now. It just takes a little bit.
There's something. What is it? Something. You don't understand?
I do understand.
You sure?
Yeah. I need a second to get it.
Okay. Let's do it here. We knew the charge on it, and we knew its equivalent capacity. When you have a capacitor, an equivalent capacitor, look at where it came from. This obviously came from this branch, right? Okay. This obviously came from this branch of capacitors. Let me just erase stuff so we can see what's going on. It came from here, right? We got this capacitor, this one, capacitor, it's that one. This capacitor is the equivalent capacitor for all these 3, right? So we know that this point to this point is the same as this point to this point, right? We found Q total because we said they're in series, they share the same Q. And we know the capacitance of that equivalent one. So the voltage of it is going to be VAB. We find it from C and Q.
C at that point and the Q total.
C is capacitor, yeah. Don't confuse yourself with this term because voltage, for example, you can't ask for a voltage of a point. That's not fine. Voltage is a difference between 2 points. So when you're saying this has 12 volts, with respect to this point has 0 volts. This one has 12 with respect to this. So that's 12 volts above this point. That's why they ask what is voltage difference of A and B.
Oh, okay.
Because if you go like here, this is 12 volts, right? This is 12 volts. With respect to this point, this is going to 0 point. 12, 12, 12, 12, 12. If they say the voltage of this capacitor is equal to 12 volts, that means the voltage difference between the capacitor is equal to 12 volts. That means the voltage drop across it is 12. So across it, it's going to be 0. 0.
The
0,
voltage
0.
difference is different than if they say the voltage
There's no meaning for voltage.
Okay.
Voltage has to have a reference point. If they ask you for the voltage, they're going to ask you, what is the voltage at the point A, assuming the 0 point of voltage is infinity. They're saying, what is the voltage difference between point A and point infinity? That's how all the questions are on the homework. They tell you, assume that the 0 point of voltage is infinity. That's why you integrate from infinity to something. Negative integration.
Okay, I get confused by finding the voltage sometimes also. Like if you find the voltage at C1,
The voltage of C1? This one?
yeah,
Okay.
and then you find you have to find the voltage of the combined system of C2,
Mhm.
3, 4. How would you find the voltage there
Where exactly?
at C2, 3, 4?
C2, 3, 4, so across here and here?
Yeah. and
That's the
then
same as the voltage across here and here.
Yeah. Like if you wanted to do the difference of it, you have to take the total V, which is 12.
Difference between what? I mean, we're saying, when you say the voltage, so when you're saying the voltage of C4, you're actually saying the voltage between this point and that point.
Yeah. And there are two ways to find it,
There's two ways to find it.
which is either you do the difference
There are
of
more than two
the
ways.
voltage at C1 and the total voltage.
Oh, you mean, yeah. V
Or-
minus the voltage of this minus the voltage of this
Oh,
gives
yeah.
you the voltage of that. Just look at this here.
Because C1 and C5 are equal in this situation.
So if you put one that's in the series, so in the series, is the voltage is going to drop, or anything to sums up the total.
Exactly. Look at this. Let's say this is 12 volts. Let's say we found the voltage across this to be 3 volts, and the voltage across this to be 4 volts, right? So this is a voltage rise, because it's a battery. Increase in voltage. Voltage drop across the capacitor. Another voltage drop, another voltage drop. So if we're going here, that's 12. Here's 12 volts. Here's 12 volts with reference to this point first. Here's going to drop 3. So that's 9 volts. This is 9 volts. This is 9 volts.
Okay, that's what I'm talking about. So
Yeah.
it's 9 volts that is coming to.
If you want to think about it that
The
way.
bottom needs to
C4.
switch. Switch it there on the bottom.
You can think about it that way if you want to think about it 9 volts coming. The right way to think about it is that the voltage of this point here is also 9, 9, 9, 9. So
Yeah.
voltage from the top plate that has voltage 9. This is 0, 0, 0, 0, 0, 4, 4, 4, 4, 4. That's not 14. So that's 9 and 4. This must be 5.
So you take 9 minus 4.
You take 12 minus 3 minus 4 is equal to 5. Because the sum of these is the sum of the voltage drops must be equal to the voltage gain. We're going to talk about this in 2 sections or something.
Next.
Yeah.
That means I got the homework questions right, assuming the wrong thing. Like I would do these subtractions and additions and have the right answer somehow. But it does not make sense.
Maybe internally you know what you're doing.
What?
Maybe internally you know what you're doing.
For the first part of the homework, like the first part, I had a minus, like the total voltage minus the C1.
Total voltage minus the voltage of C1.
Yeah, and
Okay.
then that somehow gave me the voltage of C4. Maybe I got the voltage wrong or something, but
But you gotta know what the voltage at C5 is.
that's what I
Yeah.
did not do when I got the right voltage.
Maybe you multiplied it by 2 by mistake. Because if you do multiply it by 2, that's 2.1, and this is also 2.1. So, you gotta deal with that.
Possibly.
So yeah, the voltage across, you were doing it the right thing, maybe you forgot about this one. Because voltage across here is just the voltage here minus these two voltages. Yeah, you're gonna talk about the voltage gain and loss in like, let's see. What is it, 2 lectures? DC circuits, potential circuits. Yeah, in like lecture 10 or something. Unit 10. Start talking about drops and gains, and this will all be easier and clearer. Is there anything bothering anyone? Anything bothering you?
About this?
About anything else?
Oh,
Dielectrics.
Yes.
There's number 3 homework question.
Is it the one with
Yeah, it says math. Did you guys get that?
magically he got it somehow, so that means I got it.
Oh, the one where?
Oh, the one right after this one?
Yeah.
Is it the second one? Yeah, I got that one.
How did you do it?
The one
I
with
need to see it.
dielectric
I need to
here?
see it. I don't remember.
No, not this one. Yeah.
Half of it?
It's like, yeah, it's like there's a little bar in the middle of it. Yeah.
Like here?
On the
Yeah.
bottom, on the bottom side. Is that right?
Either way, it
Yeah,
doesn't
the
matter.
bottom
Yeah, it
it
doesn't
takes. I could draw it.
Wait, just a question. No. This is something. Yeah, draw.
It's the homework right there in the last one. On that one. The last
Here.
one.
Yeah.
If you take the eraser, like circle around it and tap it, it gets rid of all of it. Like circle around it and then tap in the middle.
Oh, you were in the
Nice.
You just gotta like do one circle around it and then tap it.
Nice.
She has
Oh,
a
yeah.
She has a
We had a quiz.
Because that eraser gets like smaller every time you try it.
What was it called?
Wasn't there a question in the homework that had something like this though? Like,
Not on that side. Not like that. It was on the bottom side like this.
sure, there was also on the homework that has something like this. But yeah, we'll do both of them. Let me just show you the other one.
I think today we said, today is too bad. Wednesday, I think it's Tuesday. 150 or something. Yeah, 150 Wednesday.
This one.
Oh, okay.
Ooh.
The interactive.
Did you
Not
do
this
this one?
one. This one is okay.
The
This one's
interactive.
okay.
Yeah.
Why is this one okay and the other one not? How'd you do this one?
This one when you go to the help.
Wait, do you
pretty much
assume
does it
that
for you.
this one, I know you assume it's parallel, so the other one you assume it's in series. What?
Yeah, it's two different equations when you do it.
Okay.
That's how I know.
And why is that one hard and this one easy?
I just couldn't figure it out. I had like half this and that. I just did not put it in series. That's all.
So okay, let's assume we have another situation here. You know what? Let's just make it even harder.
That's both.
That's both. Series and parallel. Look, this is, what is this?
That's series.
This is just 2 capacitors. One here. Look, we draw this entire thing to be.
Isn't it parallel?
I'm gonna do it.
Yeah,
Same colors.
That's parallel.
That's parallel?
Yeah.
So the other
This is the same thing as.
It branching off too.
This one has a dielectric. This one doesn't. When you have one, like you were asking, the one you were asking about right now.
No kidding. Is that what you did?
Yeah.
What is this? I'm just trying to draw this as small as possible to make it look like this.
No, but
It's just the same thing. If they tell you this is D, this is D over 2, and this is D over 2. If they tell you this entire thing is A, this is A over 2, this is A over 2. What about this one? That's 4 capacitors, 2 in series, 2 in series, and both in parallel.
It
That's
would be the
as-
same. A over 2, D over 2, each.
Exactly. Only one of them has a dielectric. All the others don't.
Oh, in this case, what would you do first?
I'm gonna do it.
Series or parallel first?
Series.
Ah,
I think you said you do parallel first and then series.
After you do the parallel
Oh.
version, you can't, you gotta.
Oh, no,
What
You
are-
gotta
exactly.
singular values.
is this and this alone? Are these 2 parallel?
Which
Like,
is-
only these 2. Those are not parallel.
No.
These are in series, and these are in series. They're directly connected in series. And the combination of those are in parallel with each other. The only case where you can, doesn't matter where you do parallel and series is this. It's in resistors, but it also works here.
What's that condition again?
Equal to 0. VAB is equal to 0, that means the voltage across these two is equal, which means these are in parallel. Same thing for this.
And we can always,
So these are also in series, in total in parallel.
we also use it from A to B if that question was on there, and he asked for explanation because the wire doesn't carry a voltage, right?
Yeah, well, yeah. Technically, yeah, that's not exactly the way to say it correctly. So the voltage across the wire, the voltage difference across the wire is 0.
Okay. What's the difference?
Yes. But you forget about this for now, because it's really not important. I assume, I didn't see the questions for the test, but I assume it's not important for the
Nah.
years. But in like a section or two, when you start talking about resistors, there are a couple of questions for this, and it'll make your life easier to remember. What does parallel mean? Parallel means 2 elements that are connected that have the same voltage. So whatever element, circuit element here and circuit element here. If the voltage from here to here is the same as the voltage from here to here, these 2 are in parallel.
Okay,
Right?
yeah.
That's parallel. And because we said the voltage difference from here to here is 0, which means the voltage here is the same as the voltage here, these 2 are in parallel. That's why. I forgot. I can do that.
Can you my computer, please?
No, sorry.
So pretty much we just treat that as 2 separate equal, like situations then, right? You just add them together.
Yeah, and each one, so again, if it's, it depends on what you're splitting. So if they tell you, oh, it's half filled, and you have the area of it, that means half the area is filled and half isn't. So that's 2 capacitors, each with half the area. That's 2 capacitors in this area. A is equal to 4. This is filled. This isn't. D is the same thing because you're not splitting D in this situation. You're just splitting the area. So this has an area of 2, and this has an area of 2.
Gotcha.
Right?
That really simplifies it.
That's the easiest way to think about capacitors in series and parallel, actually. Because why do we just add them? When you have 2 capacitors in parallel, why do we just say the sum of the 2 capacitors is this plus the second? We know that C equals epsilon 0A over D, right? Something like that.
It's that.
It is that. Okay. D. We're just adding the areas. This is A1. This is A2. When we make it into one capacitor, that's a larger capacitor. With this is A1. This is A2. So that's A1 plus A2 over D. That's basically the same thing. That's why we add 2 capacitors. And why do we say that the current, that the charge stays the same on 2 capacitors in series? This is a charge Q coming here. Now, when they begin, the charge is neutral. there's no charge on the supercapacitors. When you hook the lamp into the battery, they start charging, right? The charge that goes in here, let's say that's Q plus, is going to induce a negative charge here, Q minus. And the charge can't leave this thing because it's not connected to anything, so it's only going to move Q minus. If this becomes Q minus, that means the positive charges, theoretically, are moving here, so this becomes a Q plus, and this is a charge, a Q minus. So if this plate is charged with a positive charge of Q, the other plate has to be negative with that charge, but the same magnitude, because no charge can leave. Charge cannot leave this thing, because it's not connected to it, except with this. So all charges are going to distribute only across this, and that makes all the charges, all capacitors in series, the same. This is just, I'm just trying to, I just like when people comprehend stuff, so this is not really, it's not going to ask for something that he cares more about how to solve something. So I just like people comprehending what exactly they're doing.
How would finding the energy stored in the capacitor with the dielectric differ from finding it without a dielectric?
C would change. Is it?
C would be bigger.
Because you're multiplying K times C. And then
How about the
change
voltage?
the energy would
Yeah.
increase. That's why they use dielectrics inside capacitors.
How about the voltage?
Voltage across it.
Across it?
C.
If the,
It depends on the situation. Depends on if you have it connected to a battery or disconnected.
disconnected.
Disconnected, Q stays the same, right? Are you just plugging in numbers in the homework? Is that why you're asking me?
No, I'm asking homework questions.
You're understanding this when I answer you.
I'm not even doing the homework.
Okay. I just want you to understand it. Alright. Sorry. I just want you to understand it.
I went through it, I
Alright.
didn't do it,
Okay,
that's
good.
why I'm asking.
Well, not good, but I mean. So yeah, if it's disconnected. No, I trust you, don't worry. If it's disconnected, what stays the same?
Q.
Charge, right?
Yeah.
Because Q can only travel through wires, through conductors. And charge can only travel through conductors. Nothing's connected to this. No charge is going to leave this entire surface. And no charge is going to come in. Which means when you disconnect it, it's going to have Q as the same. If you put a dielectric, we know that C is going to change. And since C equals Q over V, if I write one of these equations wrong, remind me because I'm not good at memorizing equations. So yeah. If you have C equals Q over V, Q is constant, C increases, that means V decreases.
What if there's no dielectric? What if there's no dielectric?
What do you mean there's no dielectric?
If you remove it.
If you remove the dielectric?
The dielectric
From
and
here?
the voltage.
If you remove the dielectric while Q stays the same, C decreases. Right? Because you're removing dielectric. C decreases, Q stays the same, V increases.
V doesn't increase.
Let's
Oh
solve
yeah,
for
yeah,
V.
sorry.
V is Q over C. C decreases, V increases, right?
Now I'm afraid to ask you questions.
No, please don't. Go, come on, more.
No,
Why?
I'm done.
Why?
I'm done. It's 4:15.
Well, it's an exam, so if you guys need more, I can give you more time.
Oh, when is it supposed to be over? It's review.
4:50 minutes. I don't know. Since it's an exam, I just don't know. No.
I'm really done.
Are you really done?
Yeah,
Really?
yeah, I have to go through it again.
Alright, then I got a quick question.
Alright.
When you have like the spheres, and then you have like either a conducting or insulating shell, how does that process of finding, like what you need to find different?
A sphere and a conducting insulating shell.
Yeah.
So a charge, so there's a charge in the middle.
Yeah.
And you have case A, you have conducting shell. Case B, you have. You're asking about how does it differ?
Yeah.
Okay. Insulating shell, I was putting it because it's filled. So, and let's say outside So if they tell you this has positive Q and this has small q, whatever, positive or negative, and this has the same charge, since we're comparing two things. Here, because as the professor says, and as Gauss's law tells us, it looks like a point to you when you're outside, right? Mm-hmm. So the entire thing looks like a point of charge, small q plus big Q. Here, the same thing. Outside, it looks like a point charge of big Q, small q, and big Q. Inside, we ignore everything outside because our Gaussian surface only cares about what's enclosed in it. Small q, small q. Inside and outside, nothing differs. Here, though, we know that the electric field inside a conductor is zero. There's no electric field, right? Mm-hmm. So the charge is also zero. These two are if and only if. If there's no electric field, there's no charge. If there's no charge, there's no electric field. Inside the conductor. Because the charge moves to cancel out the electric field. I think it's not talking about this today.
Then what's, is it the potential that's constant in there?
The potential, yeah, the potential is constant. So the potential from, if you're going from infinity to this point, it's the same as going from infinity to.
Gotcha.
So if he asks you what's the potential at A, and you're going from negative infinity to A, you go from negative infinity to A plus negative A to B. A, that's zero. No. Should go to B here.
Go to B and then B to A.
Yeah.
But then B to A would be zero, so it's really just infinity to B.
Right. So originally you're going from A infinity to A, infinity to B to A, and this is zero, so it's not going from A to B. In this case, there is an electric field, and that electric field increases as you go away from the radius. Why? Because you're enclosing more charge in your Gaussian surface. So if you have a Gaussian surface that's here, it's only going to have a Q, this Q. If you increase its size just a little bit more, it's going to have this Q and the charge enclosed here. Right?
Oh, because there's a charge in there.
There's a charge insulator. Yeah, this is an insulator. The insulator charge is distributed uniformly throughout it. Right?
Yeah.
So if you take, since you said this is charged, so if you take a small circle here, you're going to find charge in it. Not the entire charge here, but a small ratio of that big charge somewhere here, right? It's distributed uniformly. So if you take half of this insulator, it's going to have half of that Q.
Okay. Okay, yeah, that makes sense.
No?
No, that makes sense.
Sure?
Yeah, for some reason I was thinking that the Q was, I was thinking more like a conductor, that the Q was on the outside edge of it, and I was wondering where
That's
it
in
came
this
from in
case.
the middle.
In this case, the charge is distributed here and here, depending on how it works out.
But in that case, that's the whole donut that has it then.
Mm-hmm.
Okay.
That's the only thing. It's the one that has charge. And it's filled inside it also, not only on the shell. Inside out, that's what happens inside. It all has charge in it.
Okay.
This is empty space here. If you don't understand my drawing, this empty space that has a cube. So that's an insulating shell with thickness this much.
Okay.
That's one body. So Q is distributed.
That makes sense.
That's why when you go away from the radius, the Gaussian surface is going to enclose more charge, which means the electric field is going to either increase or decrease depending on its charge. So if it's in this case, it's positive and positive. As you enclose more charge, the electric field is going to increase.
Okay.
Right?
Would the E change?
Where?
If you have to find the E of a point, if I go to a point somewhere and you have to find the E.
Here?
In both cases, will they differ or will
Like,
it be the same?
if it's outside, it's the same. So outside here, if everything's the same, of course. If the radius, charge, and everything in the problem is the same, except that this is a conductor and this is an insulator. Outside, it wouldn't differ. It was just like a point. Inside, it also wouldn't differ because we're only looking at this point.
So you wouldn't differ.
It's only going to be different here, inside the body. Here, we know the electric field is zero. And here we know that there is an electric field that's proportional to the charging
How
force.
would you set up the formula then?
Take a Gaussian surface here.
To whatever distance it is
You did
to the,
this.
I remember, yeah.
Yeah. And let's say this is R, this is A, and this is B. And you have a, we don't want to do it with Q. Let's do it with something with rho or lambda. Because if it's a sphere, we can do it with Q. You want to do it with Q with a sphere?
With density.
You want to do it with density? What density? Like linear? Not linear. Surface? No. Rho is the only one.
Cylindrical.
Rho is the only one that works here.
It's a cylinder.
Is this a cylinder or a sphere? What did you say that?
I think it's fair, but it doesn't matter.
Sphere. And I like that we're solving a problem that we don't know what it is. You want a sphere? Then we'll describe it with rho. Rho is equal to Q over V. Let's say this has a row of 5 things, whatever that 5 is, microcoulomb square meter cubed. That's the rho of this entire body. Now that means you know that the rho equals Q over V, right? That means you know that the big Q, which is the entire cube, is distributed over big V, the entire volume. Right? So if you take a smaller body, that we're only talking about this now, because that's this charge that is enclosed in a Gaussian surface. Since this is our point, that's a Gaussian surface, and this is a charge enclosed in it, right? So Q enclosed that we want, that's a V enclosed. So all we have to do is find the volume enclosed. That volume is the volume of this. So if you want, I'm just going to draw it again here. We're talking about this being our Gaussian surface here. We want this volume here that's filled with red. That volume is the volume of this bigger sphere minus the volume of this smaller sphere, right?
Mm-hmm.
Which is pi 4 over 3 pi r cubed minus 4 over 3 pi a cubed, which is the same as if you factor out 4 over because in this case they gave you they gave you rho, so you don't have to find another v. Q enclosed equals v times rho, right? Directly multiplied by it, right?
Right.
I see a no on your face.
What?
I see an unhappy face.
Right, you're right.
Are you sure?
Yeah.
Look, if you don't ask, something like this might come up on the test, and you might regret not asking. So if you don't understand something, just tell me.
I do understand. You just haven't written the whole thing.
Oh, well,
That's all.
just tell me.
And I'm trying to write it in my head.
Okay. So that's being closed. We have Q so E dot dA equals Q equals over epsilon naught. Again, parallel perpendicular. Okay, I'll do it. Epsilon naught. Dot product cancels out because they're all parallel. The integration also ends up being EA because it's a constant magnitude. Enclosed over epsilon naught, divide by A, and that E equals epsilon naught is equal to, we found Q enclosed to be, this is B enclosed, that means Q enclosed is equal to rho times B enclosed, right?
Yeah.
Which is rho times B enclosed, that's Q enclosed, so that's rho times B enclosed. We found B enclosed to be 4 over 3 pi r cubed minus a cubed epsilon naught. We still have our area. The area of our Gaussian surface is area of the sphere with radius r. That's 4 pi r squared. 4 4 and 4 cancels out, more algebra, and you get an answer.
Good.
Right?
Yes.
Right. Still, yeah, you're right.
Good? Definitely good. Should have a little better. Should have a little
Not confident, man.
No, for real.
If you have more questions, I can say more. That's not a problem for me. I'm not pressuring you guys to say. You can leave whenever if you have something to do.
All the questions I can think of right now.
Easy one over. I needed to go over this. This is what I had trouble on. No, Gauss's.
I don't know if these will be much use for you, but if you do want to try to understand what's, like, analyze it for 5 hours or try to pick up something useful from it, I can email it to you.
No, I'm probably gonna just go home and do the.
Yeah, I don't know how useful it's gonna be, because look at that.
Yeah.
Just practice again.
Is doing the homework again or doing just the checkpoints fine after you do it?
I did
Remember
that.
you-
I
the homework?
prefer doing it. Checkpoints are more of concept tests. Homework is more of, yeah, of problems.
It's a lot of homework to give back to
It
you.
is, I never did.
All the other ones?
I do all the homework, if I don't,
With the one in the middle, right?
now I missed
With the lines.
one homework,
It'd be the same thing as
I
this though.
kinda finished another one.
They just.
But I feel bad, I still have to do it, I wanna do it.
Yeah,
Zero inside of it.
Yeah, I think it's the same thing. Yeah, but
Hold on, let me give you one.
And it'd be and just, or it'd be whatever they tell you to be. It could be omega.
I think I'm good. Yeah. I'm good. For the, just to make sure the insulating slabs or the conducting slabs or whatever,
Connect
that would
that.
be the, pretty much the same process as the conducting, shell, right? So you just break the integral kind of thing?
Basically, yeah. But here's the thing.